Hey everybody, welcome back. Today we're going to work on Unit 17, Types of Electric Motors in our Refrigeration and AC Technology textbook out of the 8th edition here. Unit 17, all different types of electric motors will be covered in here with a lot of focus on the induction type motor. An induction type motor utilizes AC electricity. It can be either single phase 120 volt, single phase 240 volt, or three phase of some different voltages as well. Some of these motors along the way can be wired for dual voltage capabilities, meaning you can hook it up to either 120 or 240 or different voltages as the manufacturer has approved it for. So without further ado, let's go ahead and get on into it. The first figure today that we're looking at is 17.1, A and B here. A is just your induction motor on the left here, where you have a belt-driven blower. You can determine that it's belt-driven because of the pulley system on the left there. And it appears that this motor up here at the very, very top has a capacitor connected to it. Some motors will have that, some motors will not. It depends on the load characteristics and the design and everything, all the requirements for that motor. Compared to figure B here is the induction motor is connected to a pump, and in this case this pump is most likely going to move water, but they're not limited to that. They could be moving water, refrigerant, oil, those types of things, just depending on what the pump is rated for. And of course, the horsepower requirement necessary to turn that pump would be determined from those manufacturers to be sufficient to handle the load. Let's go on to the next. Here in figure 17.2, this is a cutaway of an electric motor, an induction motor at that. So there's some components here that I'd like you to take a look at and try to memorize the best you can. Keep in mind this is an AC motor, AC induction type motor here. So on these motors, we've got some components here. Let's go around and take a look at it. We've got the shaft here on the left, and the shaft's purpose is basically to convert electric energy into a rotating energy here. And a lot of times on that shaft there will be that keyway cut in there, as you can see on this diagram, and from that you can connect either a pulley or a gear, whichever you want for your system to run on. On the other side, we have what they refer to as the end bell, and they're actually on both sides. We've got two end bells on this particular motor. The end bells are basically the casting or the housing which hold the bearings and keep them centered inside the unit. A lot of times these end bells will be held on by 4 screws, bolts that go all the way through the motor. What I recommend is very important if you take these apart is you give yourself some lineup points. Either take a punch and punch a point on each one of them. So like say do 1 point on this side and 1 point on this side of the seam over here, and then do the same thing on this other side though. Do like 2 points, 1 point here and here and 1 point here and here, and keep them right in line. Another method to that would be putting scribes, using 1 scribe across it and then 2 scribes on the other end, in order to that way when you put it back together it's easier to line up and make certain everything stays true how it was supposed to be. So like I say, the end bells basically hold the bearings. You notice there's a bearing in each end. Different types of bearings can be used: ball bearings, Babbitt bearings, friction type bearings, whichever. So from there we're going to take a look at this stationary part here, referred to as the stator, and the stator holds the winding. So the stationary part, the stator, is the outer shell of the motor, the non-rotating part, stationary stator. So like I was saying, inside that they hold the windings. Kind of hard to see them on this picture, but usually those windings are of copper and relatively small gauge wire, depending on the horsepower of the motor. The next thing is we have our rotating component, which is connected to the rotating shaft of the motor, and they refer to that as the rotor. So this whole internal section here in the center will rotate via induction. There is no connection from the field out here, the rotating point out here, to the center. It's all because of magnetic induction, and we'll get to that in a second. And then lastly is the frame or the base of the motor, the mounting area where you will connect that motor. And there can be some different types of mounts utilized along the way. So these are some of the components that are in here. It's not a comprehensive list, such as things they left out as the fan and the start switch, and those. This one doesn't appear to have a start switch on it. So I'm assuming it's a three-phase motor at that. So, all right, let's go on. Here in figure 17.3, we've also got an AC induction motor. The only thing now here with this induction motor is that they've drawn it a little differently, and rather than having it as a cutaway, they've got it taken apart where the end bells are separated, displaying how the rotor can be pulled out of the stator. This does a nicer job of displaying, I think, the windings in the stationary part there in the housing. The stator's in the housing there. And that creates the magnetic field, which induces that rotating force into this rotating rotor. It makes the shaft spin on there. So again, you can see the bolts that go through it. This one's only got 3 bolts in order to attach the end bells and sandwich everything together in that stator housing there. So end bells, the rotor, the stator, those are probably your biggest components of the system. It does have this bump out here. Most likely under this bump out would be a capacitor. So a capacitor type motor, whether it be capacitor start, capacitor run, I don't know for sure, but we'll kind of look into that. I notice there it doesn't appear that there's a start switch, so I would have to assume that it would be a permanent capacitor or capacitor run motor. Let's go on to the next one. Here we're looking at figure 17.4 in the text, and what we've got is we've got a horseshoe magnet and a bar magnet. As most of you know, that opposite poles are attracted to each other, and like poles will have a tendency to repel. And this is really the internal workings that makes the shaft rotate on the motor as well. When you have opposite poles, they will be attracted to each other, and like poles, they will repel. So if we look at this, in the horseshoe portion here would be our stator, the magnetic field created by the stator windings in our motor, the lines of flux flowing from north to south in the horseshoe. It is going to create a rotational field in this bar magnet, and therefore the north is going to want to move up and around and be more attracted to the south. So if we look down there, you can see that is exactly what it's doing. So what we're looking at here is we've got a rotating part inside our motor that would be referred to as our rotor for an AC motor. And then, of course, our stationary part, our horseshoe here, which is non-rotating, and that would be our stator. So the same concept that we're applying here with the magnetic fields, like poles opposing and unlike poles attracting, is how we create the rotating motion out of our electric motor. So here in figure 17.5, this is a sketch of what they refer to as a squirrel cage rotor, or aka the rotating part of the motor. As we discussed before, the poles will be attracted, and like poles will want to repel each other. So if we're looking at this, what we're going to do is from the stator, which is not drawn on this diagram, it is going to induce a magnetic field into this secondary winding of a transformer, if you will, and it'll create a magnetic field in this secondary coil. The reason they call it a squirrel cage is because it looks very similar to a squirrel cage where we've got a winding. In this case, it would be a solid bar going through there, acting as a winding, and then connected to the end rings, the shorting rings, and then connected with a different winding, aka making a coil or a winding inside of the rotor there. It will have a magnetic field produced on it because of induction, similar to how a transformer works, where no electricity actually is physically connected in here, but due to the principles of magnetism, we can induce that field into that rotor. So anyway, this is just a cutaway, a sketch of the simple squirrel cage rotor. How the bars are connected to the end rings, the copper end ring in this case. Obviously, it can be aluminum as well, I believe. I have seen some of them, but they're stating this one is copper as well. So Let's go on to the next one. So the next figure here, 17.6, they're trying to address a different question. If we refer back to the figure of the horseshoe, we'll be stating there, well, that only gives us a half a rotation. How do we get the 360 degrees of rotation out of our motor and keep that thing going? And that is related to the AC alternating current that we connect to it. If you recall, with AC current, it reverses direction and it changes direction. So if you recall, 60 hertz, 60 times a second, it has that change in direction there. And with that, when the AC current reverses direction, so does the magnetic field in the poles. The north and south pole will also reverse direction. So it continuously does that, and therefore we have a rotating magnetic field, and it's constantly changing direction and magnitude in that particular motor. So that's what they're trying to display here. Say at this point in time, the left side of the motor is the north, and at this point in time, the right side of the motor would be the north, depending on the cycle and the time that it's peaking with that. So from this AC current that we put into it, we can reverse the magnetic field and continue to keep the rotor and the shaft spinning. This next image here, 17.7, this is a nice little cutaway of what the windings actually look like in the stator, the stationary part or the frame of the motor there. A couple things to point out here is that we've got a start winding. Keep in mind that the start winding is usually going to be a smaller diameter or gauge wire, but longer in length. Therefore, we usually have higher resistance. And then the run winding will usually be larger gauge wire and shorter in length. And it stays in the circuit for a longer period of time. Therefore, the run winding, being it has a larger gauge wire, can usually handle being in the circuit longer and be able to handle the heat and the load that is put on it. Versus the start winding, they will usually only be in the circuit, only energized in the circuit until the motor comes up to about 75% of its speed there. So keep this in mind when we're measuring these windings. The run winding will generally have a lower resistance because of the larger gauge wire and shorter length of wire. In the start winding, on the other hand, will have the higher resistance because of the smaller gauge wire and the longer length. So anyway, this is kind of a cutaway displaying how the windings get put in there with some slot paper and some string. They're all tied in and bundled real tight in the stator stationary part. And this will create the poles of the motor, and then the poles will reverse with the AC current connected to it. Here in this figure 17.8, what we're looking at is a component that the rotating part of the shaft could be connected to in order to create some linear motion. In this case, it's connected to a piston on a compressor. Most likely this would be a refrigeration compressor, but I suppose it could also be an air compressor or a pump of some sort, water pump possibly too, with this system here. But as you can see, this particular system is always going to start with that piston under pressure when it starts. You know, it's leaving at 155 psi gauge there and 5 psi entering the system, so it will always be starting under a load, which may take a little bit larger motor. Compared to the next diagram, this fan here in figure 17.9, the fan would usually not be starting under a relatively heavy load. It would just have the air pressure that is in the duct there that it would have to overcome. So from this, you got a couple different motors and different designs and styles. So that's where we'll stop for this one. We'll pick up with 17.10 on the next one.